Hey guys, this is a video on C3C4 recap. So it's just going to go through quickly everything we learned in the C3C4 topic. It's not meant to teach you the whole unit though, because we've already spent like a few weeks doing that. So this is just kind of a review. If you need more specific stuff, then I would suggest that you go back to earlier videos that showed you how to do everything. This is just a recap. Okay, so in C3C4, the first thing we learned was equations of lines. Equations of lines. And we did this in 2 and 3 space. 2 and 3 space. Okay, so the different types of equations of lines that we learned are, so we talked about vector equations. And those exist in 2 and 3 space. So an example of a vector equation in 2 space would be xy equals, first we would have a position vector, so like 2, 1. And then we would have a parameter t, it's just a scalar, and a direction vector, so like -3, 5. So basically, if we had a line in 2 space, the direction vector would just be the, pointing to, okay, let me just show this. So -3, 5 is here. So our direction vector is like this. So that just means that's going to be parallel to our line. And 2, 1, so 2, 1, that's going to be position vector. So we know our line actually would be this line here. It's going to be parallel to our direction vector. And our position vector is going to give us a point on the line. So that's how vector equations work. And in 3 space, they would just also have a z coordinate. And then parametric equations, they're just when you isolate the x, y, and possibly z if it's in 3 space. So it's where you just take x equals 2 minus 3t. And y equals 1 plus 5t. So those are parametric. And and in 3 space, we would just also have a z component. Symmetric equations, which I would say we mainly use in 3 space, would be where we isolate the parameter t from our parametric equations, and then we equate them. So in the first equation, we would isolate t, so it would be x minus 2 over -3. And then if we isolated t in the second one, it would be y minus 1 over 5. And then we just make the equations equal to each other for symmetric. And of course, if it was 3 space, we'd have a z component also. Okay, and then the final one is scalar. And this one's only for 2 space, not 3 space. And scalar equations are when you can go from symmetric and just cross multiply. So we get 5x minus 10 equals -3y plus 3. So 5x plus 3y minus 13 equals 0. So that'd be your scalar equation. And another note about scalar equations are the coefficients in front of xy are always perpendicular to your direction vector. So our direction vector is -3, 5. So we can tell they're perpendicular because if we just did the dot product, so -3 times 5 plus 5 times 3, that would equal -15 plus 15, which is 0. So therefore we know they're perpendicular. Okay, so that's a whole bunch of stuff about equations of lines. So you should be able to create equations of lines given some kind of information. So for example, if I gave you 2 points on a line, then you should be able to create vector, parametric, symmetric, and scalar equations by getting a direction vector, getting a position vector, and just subbing that in. Okay, next topic is equations of planes, I guess we also did. Equations of planes. And this is going to be in 3 space. So equations of planes. So we have vector, parametric, and scalar equations of planes. So So, for example, vector equations of planes. This time we said when we define a plane, we need two direction vectors because one wouldn't be enough to define a unique plane. So for our vector equations of planes, they look kind of like this. X, Y, Z equals, we would still have a position vector that points to a point on our plane. So like 1, 2, 4. And then we would need to have two direction vectors. So it would be like plus T, 3, 0, 1, plus S, negative 2, 1, 5, for example. Sorry, I couldn't put that on one line. So vector equations would be similar to vector equations of planes would be similar to lines, but they have the two direction vectors, which you need. And then parametric are found the same way as with lines. So you're just isolating x, y, and z. So for example, in this case, x would be equal to 1 plus 3t minus 2s, and y and z are the same kind of thing. And then finally, scalar equations of planes are always in the form ax plus by plus cz plus d equals 0. So that's a d. And we know that a, b, and c are our normal vector to our plane. So they're a perpendicular vector to the plane. So to get the scalar equation of a plane, we can take our two direction vectors that are parallel to our plane, and we can actually do the cross product between those two vectors to get our A, B, and C values. So if you do cross product between your two direction vectors, because like picture a plane, if you had two direction vectors on your plane and you do the cross product, it's going to produce a vector that is perpendicular to both of those vectors, which is what A, B, and C are. So you would find A, B, and C by the cross product, and then you would be able to sub in, for example, a point into X, Y, and Z in order to determine D. So that's how you can come up with the scalar equation of a plane. Okay. So yeah, I'm not going to do that, but that's what you got to know. And then we got into a whole bunch of intersection stuff, which is the rest of the unit. So we did intersections of lines. And we did intersections of lines in 2 space, and we also did them in 3 space. So we saw that in 2 space, lines could intersect one time. They could be coincident, so like the same line, or they could be parallel. So we had 3 cases in 2 space, whereas in 3 space, we added a 3rd case. So we had all those identical cases, so same. Plus, we also had a 4th case, which was hard to demonstrate here, but we called it skew lines because they actually are not parallel, but they don't intersect. So you can't have that in 2 space, just 3 space. Okay, so just a how-to on intersections of lines. We're basically using our grade 10 math skills of substitution or elimination in order to solve for a parameter. So if you had 2 lines, which I'm just going to make up right now. So if you had a line like 3, 1, 2 plus 4, 1, 0, and then you had another line. I'm not going to do this whole question because I don't want to make this video like 4 hours long. So here's your other line. So right off the bat, if you're trying to figure out how these 2 lines interact, like do they intersect or are they parallel, your first step should always be to compare the direction vectors to see if they are parallel. And the way you're doing that is you're just seeing if they're scalar multiples of each other. So like just look for a relationship. Like, how did this 0 turn into a 4? I don't know. How did the 1 turn into a 2? Maybe it got multiplied by 2, but the other ones didn't. So clearly they're not scalar multiples. So first you want to determine if they're parallel. These are not parallel. So we know that they're either going to intersect or they're going to be skew since it's 3 space. So your next step would probably be to just try to solve it. And the way we've been solving it in class are we took each line and got its parametric equations. So x equals 3 plus 4t, y equals 1 plus t, z equals 2 plus 0t. And then we did the same for line 2. And then our next step was to actually sub the equations into each other. So to actually merge these equations and say, well, if they do intersect, then they'll have the same x values. So we're just going to equate those. So we're going to say 3 plus 4t is equal to negative 3s. So that's our first equation. And we're going to do the same thing with y and z. And then we're going to use substitution or elimination with 2 equations at a time and solve for s and t. Then we subbed them back into our third equation to check to see if it was indeed true for the values we got for s and t. And then we subbed them, if it was true, then we subbed them back in to our parametric to get our point of intersection. So there's a whole video on that if you're like, what? I don't even remember. Okay, moving along. Then we also talked about intersections of lines and planes. So we talked about how there's 3 cases. So there's the intersection point where the line intersects it at a point. So you're looking for that point. There's the plane and the line that are totally parallel. They don't intersect. And there's the good old coincident one where the line is actually on the plane and there's infinite points of intersection. I found that lines and planes were one of the easier ones because if you actually had the equation of a plane in scalar form, so like 2x plus 3y minus 4z plus 1 equals 0, and you had the line in vector or parametric form, if we always put the line in parametric form, say, then we can actually just sub the parametric into the plane. So it becomes like 2 bracket 3 plus 2t plus, and so on. Again, I'm not going to go through how to solve all these because there are individual videos out there on my channel or on our hub page. But yeah, basically we subbed them into each other and we solved for t. And then we subbed t back into our parametrics to find the point of intersection. And to tell if our line and our planes were parallel to each other, if you recall, we were able to check. So if you check your line's direction vector, so think about it, like your line's direction vector is going to be going parallel to the line. And then if your plane's in scalar form, 2, 3, negative 4, we know that in scalar form, that vector is going to be perpendicular to our plane. So therefore, if we did the dot product between this and this, so if we did the dot product, then it should equal 0 if they are parallel, because this would be perpendicular to this. And we know 2 perpendicular vectors have a dot product that is equal to 0. So we could actually check by checking the coefficients and doing dot product with the direction vector to see if that equals 0. And then we know they're parallel and it will be like one of these 2 cases. Okay, so that was intersections of lines and planes. And we also did, the very last day, intersections of 2 planes. And we found out that there's 3 cases. So you could have 2, oh, I can't draw this. I should have practiced. I really can't. Like, I just don't know. No, I can't do it. I don't know why. It takes me a long time. Okay, so two planes could intersect, like as if you, like if you took two pieces of paper and put them together, the two planes could intersect in a line. Why can't I draw that? Okay, I'm just trying again. I'm sorry, this video is going to be super long because I can't draw. It's not looking great, eh? Okay, I'm in. Getting like notification city over here. Okay, yeah, that's not working out. You can visualize it or go back to the video where I spent a really long time figuring out how to draw it. Okay, so they can intersect in a line. So two planes can intersect in a line. Or they can be parallel to each other. So you can have parallel planes that don't intersect at all. Or of course you can have coincident planes that intersect an infinite number of times. As usual. And this is like a tricky one. If you remember, you should definitely watch the video if you're not understanding this one. Because, okay, let's take this situation. Well, first off, you can tell if they're going to be one of these two cases. Because if you have them in scalar form, then they're, like A, B, and C coefficients are going to be scalar multiples of each other, right? So like if you had a plane that was like 2x plus 3y plus z minus 1 equals 0, and then you had 4x plus 6y plus 2z minus 2 equals 0, you can see that the second plane is just a scalar multiple of the first plane. So we know that these planes are actually going to be coincident because it's just this guy right here is just the first plane multiplied by 2.
Why?
Because if this D one is different though.
Why are you talking to me?
I'm talking to my class. If the coefficients.
What do you want to draw?
Okay, I gotta finish my video. So if these coefficients are all scalar multiples of these, so they're all multiplied by 2.
3 plus 3, is it 10?
3 plus 3 is 6.
Oh.
So if these scalar multiples are all multiplied by 2, but then the D value is not a scalar multiple, then they must be parallel planes and not coincident.
Mama.
Okay, so we cleared that up. If we want to figure out if two planes intersect in a line, though...
Can I go on my iPad?
Yeah, you can check it out. If we want to figure out if two planes... 2x plus 3y plus z... x minus y plus 4z plus 2 equals 0. So if you want to figure out how two planes intersect, remember we came to the problem with like, we have two equations but 3 unknowns. So it's almost impossible to solve it. So if we like subtracted or added the planes together, we're only going to be able to get rid of like one variable or two variables, I guess. And then, so we're always going to have to let one of the variable equal a parameter. So remember that? There's like a video if you're totally stumped, but eventually we got to the point where we were like, let's just let y equal t. So you always have to let one of your variables equal a parameter. Okay, and then, sorry. The only other thing that we did in this unit is the distance from a point to a plane, I think we did. Yeah, so we did the distance from a point to a plane. So if you had some plane and then you had some point over here and you wanted to figure out, what's the point here? You wanted to figure out this distance, like how far is this? We also did that too. So I think there's a video on that. But just a quick reminder, this point right here, you would have it. So let's just say it's like 3, 2, 1. Sorry, these are horrible estimates. And then for your plane, you know the scalar equation of your plane, let's say. So like 2x plus 3y minus z plus 1 equals 0. So what you need to find out is that point right there. So the first thing we have to do is we have to figure out the equation of this line is. So we know the direction vector of this line, because it would be 2, 3, negative 1. It would be the coefficients since it's perpendicular. And then we also know points on the line. So we're actually able to get the equation of the line. X, Y, Z equals 3, 2, 1 plus t 2, 3, negative 1. So we come up with an equation of this line here. And then our goal is to figure out where this line intersects this plane so that we're able to get this point right there. Once we get that point, now we're just figuring out the distance between 2 points, which is really just the Pythagorean theorem, and then you're done. So that's everything from the whole C3C4 unit. So you need to make sure you can do all of that stuff and variations of that stuff. So I put out a bunch of worksheets, so make sure you're doing textbook questions, worksheets, because sometimes questions are phrased weird. Like these are the general concepts, but if you don't completely understand them, then you'll definitely have problems with a lot of the questions on the test. Okay guys, so after watching this video, just keep following along with the instructions on the hub. Good luck.